Okay, so last week we were looking at the design practice. After we have just looked at the combination of loading, axial plus bending, and we have looked at this first equation is just basically the combination of axial capacity plus the bending capacity in plane and out of plane, and the in plane we had the square term, which I think we were explaining the nonlinear capacity available for both in plane and out of plane, but the recent studies showed that the out of plane it's becoming unconservative, so we have just removed it. And also we have the second equation wherein if you have the enhanced capacity, or in case of capacity coming from various other options like x, k or y, you could add them together and then finally divide by the total applied load divided by the capacity, you can get the unity check ratio. So one thing you must easily can see from here is the classification of joint only affects the capacity of axial direction, whereas the moment capacity not so much, except some empirical formulas are different for different, but otherwise this formula is universally used for almost all types of joints, and you can find out what is the unity check, and if the unity check is less than 1 then it is safe. So this is just a highlight of what we were trying to do for a design of a tubular joint, but of course with several restrictions, and these were the list of the design practices normally followed. The first one was design based on axial loads. Basically that means you do the analysis, you get the loads, you try to take the loads from the global analysis and put that into the design equations and see whether the unity check is less than 1, safe or unsafe. The second requirement was by the API, as I explained last class, is basically to see that even if the member stresses or member loads are smaller, very small, since you have oversized a member, or you might have actually put the member which is not required so much. For example, typical case will be procurement. You buy a pipe which is bigger than, because it is available, and you put it there, so the loads will be smaller for that particular size. So in such cases basically you should make sure that you take the 50% of the capacity of the member instead of loads, because the load is so small and you do not want to make that joint to fail. So this is called a capacity check, and it is mandatory. And the last one basically the design configurations. If you see the sketch you will understand how it is going to be configured, basically the length of the section. If you go to the next page you will see that how much is to be extended, whether you extend full length, that is the best basically, but then you do not have an optimization because your wall thickness required at the junction is always going to be bigger because of the local effects, whereas the global effect, the member is not requiring so much thickness. So basically how much is to be determined by the minimum requirement, and normally we go for d by 4, as I see from the previous requirements of the code, either the diameter by 4 or 305 mm, whichever is smaller or bigger, must be bigger, smaller is not correct. So if you find the d by 4 is coming as 500, you have to use 500, not 305, but if the d by 4 comes less than 305, then you must use 305. So basically that is the regarding the eccentricity we will see later. Basically if you have the non-concentric joints, then you have to model the eccentricities to generate the additional moments. So typically if you see the yellow color, I hope you can see the color, the yellow color is the increased thickness just made to resist the local loads. Now imagine if this whole member, the whole jacket is made of a single thickness, you do not need to worry about this effect of so called reduced chord length, this because we have reduced. If you have completely everything is same thickness, bigger thickness, then this check is not required, but of course that is not economical. So we make it as required. Of course anybody can guess, you need to provide the thickness up to at least the footprint of the brace, for sure you need, but that will not help because the load will try to distribute across the length. So you need to extend little bit beyond, and that is where we have this criteria called d by 4 or 305. Now is that enough? This is what we are going to see, and basically it is not enough, because all the empirical equations which we derived, we saw that QF, QU and the combination of them to calculate the capacity PA. I think all of you remember the formula, no? So formula for PA, formula for MA, those formulas were developed based on the assumption that this length from here to the end or the yellow color, the extended can is 1.25 times the diameter. That was the assumptions they made in the equations. Now, if you provide minimum as 305 or d by 4, capacity will be smaller or bigger? It will be definitely smaller. So, there will be a reduction that you have to apply to the calculated value of PA. So, that is what we are going to see. There is a reduction formula. If you see this formula is to calculate the reduction in the capacity, because we are not providing 1.25 on this side, 1.25 on the other side, that means making them 2.5 times the diameter. We are not providing. Of course, if you go and provide, nobody is going to prevent it, but that is going to be a extra weight, extra steel. So, what we try to provide is what is mandatory, because this 2.5 times the diameter is not mandatory, it is left to the designer's choice. You can go and provide 2.5 meter, 2.5 diameter, but nobody is going to say anything about it, but it is not going to be economical design. But what is mandatory is this d by 4 is mandatory. So, once you provide d by 4, that means 0.25 d, is not it, instead of 1.25 d, that means you are going to reduce the weight, but then the consequences of it, you have a reduced capacity. So, basically using this formula you can find out. It is a very simple, you see here the ratio R is the length of the card divided by 2.5 d. So, as long as you have 2.5 d, what will happen? R will become 1. So, you can go there, when once you put R is equal to 1, the second term will disappear, is not it. The first term is 1, automatically the calculated capacity PAC, just I have given a different symbol so that you understand. So, PAC is the calculated capacity multiplied by a reduction factor. The reduction factor always have to be less than, it cannot be greater than 1 for sure. So, it will be less than 1 or equal to 1. When it will become equal to 1? When the length of the card becomes 2.5 d. I think very simple idea. Also, you see here the parameter on the second side, the second term, you can see the ratio of nominal thickness to the increased thickness. So, if you go back to this picture, nominal thickness is the black color one somewhere here, that is the reduced thickness, whereas the yellow color one is the increased thickness. As long as the ratio is kept 1, what will happen? Does not matter whether it is 2.5 d or 3 d, does not matter, because everywhere same thickness. So, the equation also will converge to the reduction factor should be 1, that means no reduction. So, as long as you play with these two parameters, the longer, thicker, your capacity will enhance, and that you can actually do a plot. If you see this plot, the thickness ratio is equal to 1, which is basically the this line. When the thickness ratio becomes 1, does not matter whether it is 2.5 d, because it is everywhere same thickness. So, your reduction factor or the multiplication factor is 1. As long as you have the thickness is smaller, that means the ratio is smaller, you got a bigger problem. So, you can see that various lines. So, it is always going to start from 1 and come down to. So, for example, if I keep the L by 2.5 d is basically the ratio is 2.5 times, then it is automatically 1, and you reduce it, you can keep on coming down to lesser values 0.2, 0.3. So, this needs to be taken into account before you go and use this values of PA in this equation. You have to look for the reduction and then put it here. If your length is 2.5 diameter, then you do not need to reduce it, directly can use it. So, this thickened cant effect must be carefully calculated, but of course, this is only applicable for axial load. No reduction is suggested by API for moments, whether it is in plane and out of plane. This we have already, I think I have explained in the previous class as well in the starting of just now. Basically, the reason why we do this is to create extra reserve strength in the joint. That means we design for 50% of the brace capacity in addition to the actual load. Suppose if your actual load is higher than the 50% capacity, it is not a problem, but as long as your loads are smaller, but you still design for 50% capacity, just to make sure that the joints are having additional strength. That means the joints will not fail before the member fails. The last one before we jump on to basically stiffened joints, sometimes you do experience such type of 3-dimensional joints, unable to classify into any of these categories because they are not concentric, they are not going and joining to a single work point or the vicinity of the work point, and they are separated by, you see here, the separation between the top 2 braces and another brace, and both of them are, all 3 of them are oriented in a 3-dimensional angles. You have 2 of them like this, another one in another way. You are unable to classify because this distance between the top 2 braces and the bottom brace is quite far, and you could not actually treat them separately also because they are in the vicinity, they are in a kind of in between, neither of them you could classify. Such type of joints you may experience in some times, and all of them are going to carry either tension or compression. Sometimes you experience such type of joints. In such type of cases, people were suggesting do not classify into K, Y, T joints, you can actually do a 3-dimensional analysis. Some of the papers published suggest that so called the ovalizing parameter, that means each of the load is going on to the card and trying to ovalize the pipe. So, you calculate the equivalent ovalizing parameter which will be less than 1, and cumulatively you can take the effect, but API only give you suggestion that you can attempt to do this, but in practice nobody does this because it is quite complicated in a way. So, this is an empirical formula given by API that you can use. So, summation of all the loads from all the braces divided by the brace in question. For example, J is the brace in question, and basically there are number of braces from I is equal to 1 to n. So, 3 braces, it will be 3, and you are trying to calculate the ovalizing parameter. The effect is, if there is no other brace, the effect will be 1, and if there are few more braces, this is the formula that you need to calculate, multiplied by 0.7. So, it will be incremental to that brace load, but of course in real design practice we do not use it, but in the research studies, especially when we do experimental analysis, we try to use this, the effect of one brace on the effect of the cord due to various other braces in the vicinity. Sometimes you get into this kind of situation. See here on the left side, you see it is called a, this is not an X brace, though it looks like almost like X brace, but you see here there is a member going through at the center and all 4 of them giving adverse effect. 2 of them is actually pulling and 2 of them is compressing, and you can neither classify this into either one of the category called K, Y or T because the cord member is perpendicular and all the braces are in the outer plane, and such type of cases this ovalizing study will be very useful. If you go and do this analysis by taking cord, for example you take this cord and treat one brace by one brace, which is absolutely not correct. Even anybody can conclude because they are simultaneously applying 2 members on tension, 2 members on compression. So, there will be effect of 4 times, isn't it, which will not be taken into account when you do a classification as T joint or a Y joint and come up with a design, and basically say thickness is 20 mm, but actually you may need more than 20 mm because all the loads are simultaneously applied at any one given instant of time, and that is the kind of things you may experience in some design cases. You may have to check using this type of cumulative effect. The offset that we were talking about earlier, the last point in here, offset or so called eccentricities, normally we try to avoid that, but if we cannot avoid, then what else we try to do is, for example you have this case where the joint is separated by a distance of E. If this distance is quite small, how much is quite small? Basically the diameter divided by 4, 25% of the diameter, then you do not need to really worry about it because the moment introduced by this is going to be small. Those type of moment is already taken into account in the empirical equations, whereas if it is exceeding that, then you need to consider this moment in the analysis. Basically that is the recommendation given by API, which we need to definitely follow because the empirical formulas those who have developed have taken into account only a small adjustment or small distance between the 2 braces delivering the forces. Typical example will be, you see these 3 pictures, on the left side you see here basically this similar type of joint, 3 times 3 dots, you see the work points are so called the intersection of braces and the cord member. Now if you see here, if you model like this, what really happens is the load carried by one of the brace will be cancelled by another brace. That means one may be compression, the other one may be tension, which that means the cord is not experiencing actually the shear transfer between one brace to other brace. If you model this way, the right hand side, you will see that the member between these two small members will experience large amount of shear and as well bending moment. So that is why whenever the diameter by the eccentricity is exceeding d by 4, you should actually design the intersections or the small members between them to be correctly. So that is some recommendations you need to note, because if you forget, you may actually under design the cord member. The next one is the grouted leg joints. So far what we have seen is the joints or the cord members are purely single skin, that means only pipe is there. Now I think you might have understood already the jacket legs, we have the piles going through and we have either grouting or sometimes no grouting. So when you do have such type of legs grouted, so the grout is filled in the annulus, so you have an external steel cell and internal pile, and when you actually apply loading, it is not going to behave exactly same, but then what is the equivalent effect you can take, because there is a pile inside which is going to provide large stiffness, and they are made together by means of the grout which is filled inside and set, and they are going to behave as a composite member. So what we need to do is, the suggestion from API is to calculate the equivalent thickness ignoring the strength of the grout. I think you might have studied in your mechanics, you can always calculate the equivalent thickness, equivalent section modulus, equivalent area by means of modulus of elasticity ratio. So you can calculate that, because that is the reflective of the stiffness of the any material, so you can calculate. But what API suggests, do not use the strength of the grout, but you can use the advantage of the grout provided by the composite action of inner pipe and the outer pipe. So SRSS basically is one of the methods suggested by API, basically square root of inner pipe wall thickness plus outer pipe wall thickness will give you an equivalent thickness, which you can use in all your calculations whatever you have learned. So you have already learned how to do a design of a tubular joint. So instead of only the outer thickness, you will use the equivalent thickness, which is square root of sum of squares of the inner pipe and the outer pipe. Now there were several studies done in the past proved that, for example, you calculate the equivalent thickness and it comes more than 2 times the outer cell thickness, it is becoming unconservative. Some of the experimental studies proved that do not use the calculated equivalent thickness if it is bigger than 1.75 times the outer wall thickness. That is a limitation posed by some of the research papers, but API does not give you that limitation, but in practice we normally limit to 1.75 times the thickness. So you replace all your cord thickness with the thickness equivalent calculated here, only difference is the QU values are slightly different from what you have learned for single skin joints. I think QU for T joint was basically I think 30 beta, if I am not wrong. If you go back to the table, if you go here, let us just quickly look at 30 beta for T or Y joints in axial tension, change to something slightly different here, because of the composite action is 2.5 beta gamma times Ka. Ka is defined as something like this for tension, and for bending is also slightly different formula. So only these are the changes you are going to make to the original computation, what you have learned, the QU values and QF values, only QU values are changed because you have a cell inside a cell with the annulus filled with the grout. Other than that, no procedure is going to change because of this change. The last one is basically the overlapping joints. I think you can see from this picture, what you can notice is 2 braces are trying to be connected to one joint here, that was our intention, and because the cord size is smaller, we ended up opening up. Otherwise you see the bottom picture, I still would like to make it connect to single point, that means no eccentricity, the loads coming from one brace is taken as the cancellation effect by other brace, the cord does not experience too much of a shear, there is no unbalanced forces. So, this is good, but then I have an overlap because the diameter of this cord is quite small. Now, if I make the diameter of the cord bigger, like what you see in the dotted line, is not it, you make the diameter bigger, then I will get this much gap, is not it. If I make the diameter bigger and bigger, then there is no overlap, but what will be the consequences? The weight of the structure will increase, number one, the wave load will increase. So, basically to avoid, you can try and see this overlap joints, but the overlap joints, how to design, this is one of the major problem, because so far what we have learned is design of a joint like this, members are not overlapped, individually delivering forces in the form of T junction, Y junction or K junction, but here there is a load coming from this brace, partly loaded onto the brace, partly loaded onto the cord. Now, the sharing between them depends on how much is the overlap, and that becomes a slightly complicated. So, what we have so much learned about all those empirical equations, we may not be able to use them here, and API suggests do not use unless essential. If it is essential, then you look for a separate study, that means you will do a finite element analysis like what I have shown you earlier, try and do that kind of local analysis and then see whether you can resolve it, but most of the time no companies or no owners will actually prefer this, because you see here this weld is unable to see after you finish it, because it is inside another brace. So, you cannot see the weld, you cannot inspect it, if a crack happens afterwards, it is going to be failing, and that is why overlapped joints are not at all recommended. There were several studies in 1970s, because this proves to be one great advantage. You see the length of this can, or so called the colorful picture, the LC, the length is more at the first picture down here, whereas the bottom one length is slightly less, maybe 10%, 15%, because we have made it to overlap, but at the price of additional material being provided on this member. So, there is absolutely, actually you are not going to save too much, it is only a perception that you do a overlap joint, I will try to save this much, but ultimately the design becomes complicated, and you also have to spend some more material in compensating, because after all, if this is not having a special property, that will fail. So, that is why normally not recommended. Something like this you can see from here is a picture that you can easily understand. Overlapping becomes problem, because this member, if you make it bigger, then automatically overlap goes away, and you have to size the braces properly, so that that type of overlap does not come up. Now, basically the last one in the tubular connections in the static analysis is basically to design a stiffened joint. Whatever we have learned is unstiffened joint, and then we had looked at the can reduction length effect, then we have looked at just the multiplanar joints, and then basically the overlapping joints. The last one is the joints which has been stiffened by somehow to increase the strength. So, basically what we try to do is, if you have decided the thickness of this, for example this so called thickened can, but ultimately you do not get that kind of thickness, or you already have purchased but the loads have increased. So, scenario might come in such kind of issues. So, how do we make it safe? So, you can always go and provide stiffening inside, as usual, any structural member you can add stiffeners, you can stiffen them against any of the failure action, it can be bending, it can be shear, it can be torsion, you try to stiffen them. In this particular case, is the stiffening required against the three modes of failure we learned about. One is ovalization, basically trying to compress from circular section to elliptical section. The second one is basically a general collapse, just compressing. The third one is either pull off or just local punching failure. Now, if you see this, if you go and put inside full of concrete, you just fill the whole member with the concrete, what will happen? Nothing will happen. Basically concrete is very good in compression. So, when you try to load something in compression, it will definitely take huge amount of load, but what about tension? When you apply tension, this concrete will not come into that much effect. So that is why instead of providing concrete, you can actually provide concrete, sometimes we do use that, but then the jacket becomes very heavy, not very good. So the alternate solution is provide concentric rings under the load such that when you try to compress, the ring action will come into picture. As you know very well, rings are very good in taking arch action, the load distributed by radial will take a huge compression load. So that is why you provide a rings inside, and that rings will be catering for all the three effects. It could be punching effect, it could be pulling effect, or it could be ovalization effect, and many times we use this. Unfortunately what happens is method of analysis is not very clear, because API leave it to the designer, does not recommend that much guidance. So what has happened is over the period of time people have been using different ideas, but then the recent API does give some guidance, you could do this, you could do this, but not elaborate enough. So basically I have just summarized few of the ideas. There are several methods available. You can do an elastic analysis of ring using a finite element software, or you can use a plastic analysis of the ring, or you can use the unstiffened tubular joint equation. The third one is very commonly used. So you know what is the effect when the ring is not there, so do all your calculations, but then evaluate the strength of the ring and put it inside your API equation, and you will get the combined effect. The fourth one is basically equivalent thickness, very similar to the composite pipe we used, pipe in pipe with a grout. You can find out what is the equivalent thickness, that means thickness of the original cord is say 20 mm, the additional thickness effect due to the presence of the rings can be another 10 mm. So you provide 30 mm, you all can substitute the thickness into the conventional joint calculations. The last one, which I have been doing some studies for the last several years, come up with modification to the API equation so that you can easily design it, which we will see. Some of the publications is already available. So the first one, we need to understand how the behavior of the ring. You know, if you provide a ring something like this without a flange, you can see the red color is the ring positioned appropriately. Normally we position in such a way that if you see the plan view, something like this, you see here in this, you should understand the ring should actually be placed within the periphery of the brace. Do not go and provide outside, it is not very good, because here the load will transfer at the hard points. You see the red color point, that is the point, the cross section or the crossing of the stiffener with the wall of the pipe or the brace. So that is where the load will jump, because that is where the stiffness is higher. So you should always provide within the perimeter of the brace, and basically you see here typical idea is in the practice about 2/3 of the diameter. So if the brace is inclined, accordingly you have to calculate the elliptical diameter or elliptical dimension and then provide it. And if you look at the individual stiffener, this is what is going to happen. You know, the ring is going to carry a point load at the point where the intersection is happening, with part of the cord is also participating in the whole behavior, isn't it? Because it is not only just the stiffener alone, but also the green color. What I have shown is some part of the cord itself is going to be behaving together with the ring, and that equivalent, some empirical formula is given in practice. So you can calculate, typically it will come something like 1.1 square root of RT is an empirical formula, is not derived from somewhere. So what we need is a solution to such type of load with a ring. If you go back and look at the literature, some of the mechanics book, you will find solution to such type of, but very complicated. This type of loading you see here, if you go back, I have just provided the load transfer only at this point. What about the loads at elsewhere? You could actually decide to divide the total load P divided by 4, isn't it? And each point is carrying 1/4 of the load and do it. But if this is only true only if it is a vertical brace and also only 2 stiffeners, and it is also true only for axial load. What about moment? When you have the moment applied in this fashion, you will have 2 points carrying compressive load, the other 2 points carrying tension load. So you have to sum it up. And then what about the out of plane moment? One point will carry combination with axial plus in plane bending plus the out of plane bending. So you will see that one of the corner point, this point is going to carry almost maximum load. All other points will carry slightly lesser depending on the direction of the moment. So you need to resolve the forces and then carry out such analysis. Of course, if you look at some of the textbooks, you will find equations to solve. Basically, I think I have given one of the equation to solve is this type of formulas given in one of the book, Rourke ring book. Basically it's a Rourke formula for stress and strain. It's a compilation of all the formulas. You will find such type of solutions for calculation of bending moment, because you can, once you find the bending moment, you can always find out the bending stress. So such type of this is not empirical formula, this is derived from mechanics, simple bending of circular ring beams. So you can derive it, but one of the thing is only for simple load cases such ideas are given. If the loads are complicated, then you may be forced to go for finite element analysis. So you could either use the Rourke formula if they are very simple cases, but if they are complicated, you could use FE analysis. I think some of you might have already been doing. So you can see that they can solve any complex problems. So the allowable capacity is calculated as calculated capacity divided by again factor of safety. The reason why, even though we do elastic analysis, actually when you do elastic analysis you do not need to do basically any divide by factor of safety, because it is within the limits of elastic, but then you look at elastic means you can go up to yielding. So that means you definitely need a factor of safety to be defined. Alternatively, you could also do a elastoplastic or so called ultimate strength analysis. Some of the softwares, FE softwares are available, are capable of doing such. Basically you can load it until failure, and you can divide by a larger factor of safety. So the difference between elastic analysis and elastoplastic analysis, the magnitude of factor of safety is definitely going to be different. Here you may use 2.5 or 3, whereas the elastic analysis you will use 1.67 or 1.75. The third one is a very simple one, tubular joint strength, which actually we have learned for last few classes, plus the capacity of the ring. The capacity of the ring is calculated as the simple shear capacity. That means if you cut the stiffener across, the vertical or so called the web of the stiffener will be active in taking the shear. So basically 0.4 times the area times the number of stiffeners, I think, which we have learned about shear capacity last time. 0.4 is the allowable stress factor multiplied by yield multiplied by area, which is basically the height times the thickness, and n is the number of stiffeners. So you go back to your interaction equation, the PA is calculated as per the API plus PS is the shear capacity of the stiffener themselves. This seems to be very simple method, because you do not need to do anything, straight away use the API equations and then add the capacity of the shear of these stiffeners, and many times people use this method because it is quite simple, very easy to calculate. Unfortunately, the stiffener does not provide any enhancement on the moment capacity. So that is one of the weakness here, though it may provide, because if you go back to this sketch, definitely when you apply a in plane moment, one of the stiffener is going to get compression, the other brace is going to get tension and compensating. For sure it is going to help, but imagine if you have only one stiffener at the middle, yes, it does not have any moment capacity. If you put three stiffeners, for sure it is going to be effective. The central one will take more axial load and the two outer ones will get the moment load. So that is one of the weakness that we find sometimes people do not agree, especially the contractors. The fourth one is basically using the conventional simplified method of equivalent thickness. So the equivalent thickness can be calculated either by the moment of inertia equivalence or by the method of shear area. So if you see there, the first one, the area of the ring, which is basically this plus this divided by B, I will get the equivalent thickness. Just because the presence of the red color, basically the stem, what will be the additional thickness I will get, that is what we are doing. We keep the B same. So, you go back to your API calculations, simply replace the thickness with T equivalent, which is seems very simple, but many times this produces unconservative results because of such a simple. So, you have to calculate both T equivalent using moment of inertia and using section area, and then find out whichever is smaller and try to use this. Sometimes agreeable to some clients, sometimes. The last one is very simple also. So, we have geometric parameters for the joint, we have geometric parameters for the presence of load, which is QU and QF, and QR you find out one more empirical parameter just because of the presence of the ring. QR will be 1 if there is no ring, and QR can be a enhancement factor, which some of my students have published a few papers, so have carried out tests as well as FE analysis, come up with a similar empirical formulas like what you saw there, the plots of QU values, several plots we saw now with respect to beta, with respect to various other parameters. So, if you come up with that, you can use this. So, basically one of the paper we have published in one of the journal, which you could use that just to compute 3 stiffeners, QR value is so much, 2 stiffeners, thickness different. So, you can use that as a modification factor to enhance the capacity. So, what we have seen here among the 5 methods proposed, the one easy to use is method 3 and method 4, normally practiced because of their simplicity, and you do not need to go on to method 1. We used to do this, especially these Rourke formulas early 90s, but then they are very conservative because these ring formulas are really conservative, the moments are very high, it may require a bigger thickness. The last one, I think we just look at the material properties, because you have seen the special property at the junction. Normally we require the property such that when you pull the brace by applying tensile load, the material on the cord should have sufficient across thickness property that it does not peel off, that is what we were looking at the other day, so called a through thickness property. While doing so, actually you see there the material for the structural applications, API classify into low strength, medium strength and high strength. Basically the range of yield strength is given 280 to 360 and beyond 360. Normally beyond 360 is not recommended because of the welding is associated problems there. And you have materials coming from various specifications, American codes, ASTM, API and British codes, and now ISO codes. Most of the British codes have now been merged with the ISO codes, they are called BSENs, and basically you will find several classes of materials available for ship construction, steel for basically the structural application for offshore structures, onshore structures. So, you have to select them suitably. The primary point is what is recommended by API, you cannot use beyond 400, 400 is a demarcation given by API not to go beyond, because they expect more and more welding problems, and you will have, especially for the joints of the kind that we are dealing with. Of course, you can use elsewhere, like for example, if you have a bolter connections, nothing to worry, whereas we are having a high shrink welded connections, and that is where we have problem. So, basically the joint locations where we have highlighted as a yellow color previously in the few pictures, and that is where we need basic idea is the material should be properly selected such that the failure by material behavior does not happen. That means better material, if it fails by loading does not matter. So, that is where we have to make sure that the welding and the material selection is supposed to be correct. And one of the property that we are looking at is the through thickness property, that means when you pull across the thickness, the lamellar tearing should not happen. The second thing is the material toughness at such applications. I think in the other course we will be going in detail. Basically the toughness of the material against impact loading should be higher. So the energy of impact is to be resisted by the material toughness, which is measure of easy method of finding out is the Charpy-Bénard test of a particular specimen at certain temperature depending on the application wherever the jacket structures are located. Normally API recommends minus 30° testing and you should get 47 joules. So next time when you go down to our laboratory we can see how the Bénard test is performed. And the notation here basically Z35, Z25 is nothing but you take the specimen across the thickness and try to pull until such time the deformation is at least 35%. If it fails earlier than that, that means is the material is not very good. So basically the neck area you should get at least 35% extension. And I have given two problems I think, or one problem. Probably we will try to finish this problem before we finish the class today. So it is a typical, so all of you understand what exactly is going on the tubular connection. So we started with classification, empirical formulas and special cases and then ring stiffened joints. We will just do one simple example to just to highlight the importance of classification, and that is what the purpose of this example. So use this, one side is 406 by 12.7, the other side is 508 by 15.88 with the different angles. It is a typical joint in practice and have the chord thickness and the information is given 762 by 19 mm basically somewhere here, and with this what has been asked, find out the unity checks using the formulas you have learned using both methods Y and K joints. You could actually classify them, you have the loads in the next page, I think I have just summarized, but if you actually use Y joint and if you use K joint equations, how the equations make the results differing. And of course you will see that the Y joint, what we have learned from our conceptualization, Y joint is going to be unbalanced, K joint is going to be balanced. So balanced one should result in lower unity check, unbalanced one should result in slightly higher unity check. So we are going to just see how they are going to come. The data is summarized, of course the loading is given, each brace is 900, 1275, I have just given the actual load in such a way that they are behaving as a balanced case because the angles are different. Of course the moments are given slightly different values and there is no load given for the card, so card load factor will become 1. So to make life little difficult, easy instead of solving for those, and all other information is given there, yield strength is given, brace diameter, card diameter, wall thickness, everything is given. So once you are given this, you can straight away jump into calculate the geometric parameters like beta and then gamma and then basically the QG factor which is to be used for K joint because all of them are known, and this beta value you will have two beta values, beta value for brace number 1, beta value for brace number 2, gamma value of course only one gamma value because d by 2t, and the gap is given as 50 mm. So if you solve, I have just taken brace number 1 which is on the left side, I have just solved for QU value and then basically substituted into the PA allowable, I am just putting subscript so that PA1, PA2, so you do not get confused, and you also calculate the allowable moment capacity in plane, allowable moment capacity in out of plane, substitute into your interaction equations, ultimately you get a 88% utilization, quite safe, isn't it? So you just do all the formulas are available, so it is not a big trouble, substitution of numbers only. And I go to the brace number 2, you do the same thing for K joint, I get a unity check of 0.9, both are safe, only just I just replace the values of second brace, gamma values and so beta values and the loading, and go to brace number 1, use the Y joint method, I get a unity value of 0.994, and go to brace number 2 1.025. Now, if I go to the summary, just a quick summary to look at what really happens. I just look at the brace 1, when I use the K joint I have got 88%, I go to the brace Y joint I get about 10% higher. So, basically Y joint is unbalanced loads give you a slightly increased unity check, that means more trouble for us. So, if you do not classify the joint according to the loading, you will see that you will be doing a incorrect calculation methods. Similarly, to brace 2, 0.9 becomes 1.0, and typically just because of your method of calculations. So, this example gives you an idea how you do it, number 1. Also do a comparison. So, if you are asked to find out the unity check, or if you are asked to find out what is the capacity of the joint, you just need to go back and just calculate the geometric parameters, go to QU values and find out the QU from your beta values, and if it is a K joint you will have the QG multiplication there. If it is a Y joint you do not have that QG, and QF fortunately was given as 1 because there is no load on the card, otherwise you will have to go back to your QF equation, substitute all the parameters, find out what is QF, then you come back here, because basically you see here QU multiplied by QF multiplied by FYT square divided by 1.6 sin theta. Now, in the examination point of view, what will be given is basically this table will be given. So, you need to remember remaining this table will be given, this table for a tubular joint design. This contains only the information regarding QU, and these equations will be given, you do not need to memorize, and when I give this equation I will give you this table, because there is no point in memorizing these numerical values. So, these 3 information will be provided, and basically remaining you should remember, especially the this interaction equation you should keep it in your mind. Also the equations for calculating PA and MA you should be able to keep it in your mind, do not ask for it and make sure that you remember, but those 3 big, this table plus QF values and associated constants I will definitely provide in the exam sheet. I think so. Whatever we have done so far is basically the static capacity of tubular joint.